Ever wonder why a glass of soda fizzes, or how ultrasound therapy works? It all starts with tiny bubbles, those seemingly simple pockets of gas in liquids. But behind their bubbly surface is a world of complex physics. Today, we're exploring how scientists are using AI to crack the code of bubble behavior, and why this could revolutionize everything from medicine to industry. Let's start with the basics. Bubbles aren't just random, they follow strict rules. Think of equations like the Rayleigh-Plesset and Keller-Miksis models. These are the instruction manuals for how bubbles grow, shrink, and oscillate under pressure. But here's the problem. Solving these equations is like solving a puzzle with millions of moving parts. It's computationally heavy, especially when you're dealing with high-frequency pressures or multiple bubbles at once. That's where machine learning steps in. Researchers have been using neural networks to predict bubble behavior, but traditional models struggle with one big issue: high-frequency details. Imagine trying to film a hummingbird's wings with a slow-motion camera. The fast movements blur. That's what happens with standard AI models when they're faced with rapid bubble oscillations. They miss the fine details, leading to inaccurate predictions. Enter BubbleONet, a breakthrough AI model designed to tackle this problem. It's built on a framework called DeepONet, which is great at learning patterns, but with a twist. It's infused with physics-informed constraints. Think of it as giving the AI a cheat sheet of the laws of physics, so it doesn't just guess, it learns the rules. Plus, it uses a special tool called the Rowdy activation function, which helps it spot those tricky high-frequency details. The team tested BubbleONet in 3 scenarios: single bubbles under varying pressures, and even multiple bubbles interacting. They compared 2 training methods, single-step and 2-step. The results? BubbleONet matched traditional simulations, but ran way faster. In one test, it predicted bubble behavior under extreme pressures, up to 1 million pascals. With incredible accuracy. It's like upgrading from a slide rule to a supercomputer. Why does this matter? Let's zoom out. Imagine designing medical devices that use ultrasound to target tumors, or optimizing industrial cleaners that rely on bubble power. With BubbleONet, these simulations could happen in seconds instead of hours. It's not just about speed, it's about unlocking new possibilities in science and engineering. But this isn't just about bubbles. The same principles apply to a broader challenge in science: solving inverse problems. Think of it like this: a forward problem is straightforward, like predicting where a ball will land if you drop it. But an inverse problem is the reverse: figuring out what forces acted on the ball based on where it landed. These are notoriously hard, especially when data is noisy or incomplete. Traditional methods often stumble when data is scarce. It's like trying to solve a puzzle with missing pieces. But the new approach gives AI a superpower. It embeds physical laws directly into its calculations. Instead of just memorizing patterns, the neural network understands the science behind the data. This is where physics-informed neural networks shine. By hard-coding equations like Newton's laws or fluid dynamics into the model, the AI doesn't just guess, it reasons. It's like teaching a kid to ride a bike by explaining gravity, momentum, and friction, not just telling them to balance. The result? A framework that's way better at handling uncertainty. Whether they're modeling climate change, designing drugs, or decoding cosmic signals, this method is like giving scientists a more reliable map for the unknown. And the best part? It's not just theoretical. Early tests show it outperforms old methods, especially when data is limited. So next time you see a bubble, remember, behind its simple surface is a world of complex physics, now made smarter by machine learning. And beyond bubbles, this approach is reshaping how we tackle some of the trickiest problems in science and engineering. Thanks for watching. Hit subscribe for more deep dives into the science shaping our future.